So in this video, we're going to take a look at the laws we can use to model the pressure of a gas. So before we get onto that, we first need to have a look at a few experiments that we use to actually give us evidence of the kinetic models of matter we've been building in terms of atoms. And then what we're going to do is we're going to define something called internal energy, which is very commonly used to explain the behavior of gases. And then we'll finally finish off by looking at the factors that affect the pressure of a gas and how we can actually model the effect of those on the pressure. So let's have a look at the experiment we used that gave us evidence for the first time that atoms exist. So let's take a look. Okay, so what we've got here is essentially a setup. So we've got a microscope because all the things we're dealing with are very small, so we need a microscope to be able to see them. So inside the microscope, what we've got is a gas, and we've also put smoke particles in there, and we're shining a laser through so we can see the location of smoke particles. So let's start it off. So if we can see, we've got, this is what it looks like closer in. So we've got a laser shining through our chamber that has gas and smoke, and a microscope can see smoke particles. So where you see green, we are looking at smoke particles and we're seeing how they move. So if you actually have a look at them, you can see that very few of the smoke particles are actually colliding with each other, but they're still changing direction. So the question is, why are these smoke particles changing direction if they're not colliding with each other? So this is the experiment with gas and smoke particles and using a laser to make smoke visible. We can also do this experiment with liquids. I'll show you that too. So what you can see here is water with some pollen grains in it. So you can see we get the same thing in water. These pollen particles are not really colliding with each other, and yet they're continuously changing direction in a seemingly random way. So these experiments gave scientists some serious thought and were like, well, why is this happening? And this is where our model of the atom comes from. So on the right, you can see a simulation of how our scientific community views what's going on in those two scenarios. So in the experiment with a gas and smoke particles, the yellow blob you can see on the screen is there to represent the smoke particles that were bright green. So the black particles are our way of modeling the gas particles that are involved there, which are too small to see even with our most powerful microscopes. But if we had more powerful microscopes, this is what we'd expect to see. So the smoke particles, as you saw in the video, are continuously changing direction. So things do not change direction unless a force has acted on them. You should know that from the mechanics part of the course. And the other thing you should know is that forces come in pairs. So if a force has acted on the smoke particle, that means a force must have acted on something else as well. And that is our evidence for the atoms. So something must be colliding with the smoke particles to make them change direction, and our model of atoms comes from that idea. And the fact that smoke particles appear to move completely randomly or unpredictably indicates that these particles that are colliding with also are moving in a random fashion. So when we describe gases' motion as random, this is our evidence for that, and it's the same with the liquid as well. So this behavior is known as Brownian motion, named after the scientist who did this experiment, whose surname was Brown, and it's our actual evidence for the atomic model or the kinetic model of matter. So that's the Brownian motion experiment. Let's now define what internal energy is so we can start thinking about how it relates to gases and pressure. So in previous videos, I've talked about the atoms having both potential energy and kinetic energy. So when we're dealing with a whole system of gas particles, if we add together all their potential energy and all their kinetic energy, that is what we call internal energy. So what we can say, therefore, is that when a substance is supplied with thermal energy, its internal energy always increases. So it's our way of modeling a whole system of gas. So if we take thermal energy away from something, that causes the internal energy to decrease. We're not focusing on which specific atom it's come from. We're just saying somewhere in our system, some internal energy has decreased, and that's why we use internal energy. It's our way of modeling whole systems of gas, not the individual gas particles. So that's defining internal energy, and I'll introduce you to where it comes in a bit later on. So let's have a look at the factors that affect the pressure of a gas. So you should know from the mechanics and forces part of the course that pressure is force divided by area. So essentially we can increase the pressure by either increasing the force or decreasing the area. So you can see on here that we've got decreasing the area would be one way of increasing the pressure, and we would do that by decreasing the volume of the container. That would act to decrease the area as well. So that must mean essentially that these two things here are essentially mechanisms for changing the force that is acting on it. That's fairly horrific, so let's rub that out. But those things are there to affect the force of it. So if you increase the speed of the gas particles, that gives you a bigger force. And if you have more gas particles, that's going to exert a bigger force as well. So this is all tied in with the pressure, force, area equation. So those are the factors that pressure a gas. How can we actually mathematically model it? Well, we can do it using something called the equation of state. And the equation of state essentially says the pressure times the volume of gas is equal to the number of molecules times a constant, which has a specific value, and the temperature measured in Kelvin. So this is our way of actually modeling a gas. And just to note at this point, we don't use this to model liquids or solids. This is just for modeling gases there. And we can see each of the units that we're using to measure it. So let's have a think about what that is going to mean in different scenarios. So what we're going to be doing in the next part is I'm going to be trying to get you to work out what the relationships are using these equations. So the first thing we want to do is if the number of molecules n and the temperature remain constant, what would the relationship between pressure and volume look like? So I'd like you to pause this video now, have a think, and see if you can sketch what you think this graph looks like. Okay, so now you've had an opportunity to sketch it, and I really hope that you've taken the opportunity to have a go anyway. Let's have a look at how I would go about sketching this. So the first thing I'm going to do is I'm going to take the equation and simplify it. So if n, k, and t are all constant, I can write that just as one constant, which I've called c with a subscript t to say that temperature stays the same. So what that means is I can rewrite the equation as pressure is equal to a constant divided by volume. And that in general terms describes an inversely proportional relationship. So you can see that as volume increases, the pressure is going to decrease, and it's a specific 1/over relationship. So that's an inversely proportional relationship. So your graph should look like the one you can see on the screen. That is the graph of an inversely proportional relationship. So that's how we do it if n and t remain constant. Let's give you another one. So this time the number of molecules and the volume are going to stay constant, and I'd like you to have a go at sketching a pressure versus temperature graph. So pause the video now and have a go at sketching it, and then we'll see if you're right. Okay, so let's have a look at this one. I've done exactly the same thing. So the first thing I've done is I've moved volume to the other side, and then I've replaced n, k, and v with a constant, and I've given it a subscript v just to show you it's a different constant to the one we had previously. So we can see here that we have a directly proportional relationship, because we can see if temperature is 0 Kelvin, pressure is going to be 0, so it's gone through the origin, and we can see that it's going to be a straight line relationship too, so we describe that as being directly proportional in those circumstances. Okay, so let's try another one. So this time we're going to keep the number of molecules and the pressure constant, and you want to sketch a graph of volume versus temperature. So again, pause this video, have a go. Okay, so now you've had a chance to have a go, let's have a look at my working for this. So this time the first thing I did is I moved P to the other side to make volume the subject. I replaced NK over P with a constant, again with a different subscript just to show it's a different constant. So we can see again we've got a directly proportional relationship between volume and temperature there. So let's have a look at the last one. So we said earlier that the number of molecules could affect the pressure, so let's have a look at that. So if volume and temperature remain constant, what would the pressure versus the number of molecules look like? Pause the video and have a go. Okay, so you can see the first thing I've done is I've taken volume to the other side. I've replaced I've replaced KT over V with a constant, and again given it a different subscript because different things have stayed constant. So we can see we've got another directly proportional relationship between pressure and the number of molecules. So we can see our equation predicts exactly the same thing as we described earlier in terms of the factors that affect the pressure. So that's where I'm going to finish off this video. So these are the things you should now be able to do. So if there's anything you can't do, go back and have a look at that section and make sure you can. If you have any questions, please feel free to comment and let me know. I'd be more than happy to get back to you about them. But thank you very much for taking the time to watch.